Thank you for joining. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. Today, our webinar titled The Role of Thermal Conductivity in Solid-State Hydrogen Storage. I'll be joined by a few speakers here. My colleague, Dr. Genesis Infante, from our C-Therm team, will be presenting some data. And I'm also very excited to announce Dr. Jacques Huot from the University Quebec Trois-Rivières will also be speaking in today's session.
So the advantage of metal hydride is that you have a high volumetric density, you could work at low pressure, and the reaction is endothermic. When the metal is really releasing its hydrogen, it's an endothermic reaction. So it has a benefit for example, if you have an accident and you have a rupture of your tank and there is a fire and your tank is releasing hydrogen, then the tank will cool itself. So the reaction will be killed by itself. So that's an advantage, one of the advantage of metal hydride. But
I hope that at this point, everyone has a better understanding of the importance of thermal conductivity with the applications of metal hydrides and how metal hydrides can offer this advantages over different other hydrogen storage systems like gaseous or in a liquid form. And the challenges that are incorporated with that application. How do you test thermal conductivity at this particular conditions? And again, shown in the screen right there. The basic conditions that we're playing around here is that you'll have your metal hydrides in different type of like density quality, and under applying hydrogen into that metal hydride and typically under high pressure and high temperature. Basically, you want to test thermal conductivity with closest to what your target working condition would be. And oftentimes that can be very, very challenging. So us here in C-Therm, we work really, really hard on trying to give that capability to anyone that's interested. So just for everyone that's not very familiar in how the TPS work, the basic principles of operation is that typically the sensor is sandwiched between two pieces of the sample. That's why we're requiring you to have two of these pallets, as the TPS method operates under a symmetry kind of assumptions. And the basic premise is that we input a power into this as the sensor is also the heat source at the same time, and that heat transfers into the sample. We monitor that change of temperature over time, and then from that temperature change over time curve, we can get the thermal conductivity and diffusivity of the material. Yeah, coming back to the high pressure cell right there, shown in this slide is the pressure, on the left is the pressure cell and the associated TPS sensor. And you can see that on the right is the sample holder where we insert the pallet in there, and you'll have a spring-loaded force basically keeping the pallet pressed into the TPS sensor itself. It's very important that we maintain that compression basically on the stack. So we want to maximize the contact between the samples and the sensor itself. And also, as the cycle between hydrogenation and release of hydrogen, there is an expected change on the pressure itself because of the expansion associated with the material. So as you can see here, there is it's a whole process on how we're gonna set it up. And again, part of the guideline is, this is how you do it, and we offer all that whenever you need it. And if for some reason your requirements are more on the higher pressure range, there are options for 3,000 to all the way up to 5,000 psi options. And we can definitely accommodate that depending on the conditions that you're requiring. On the right is just the top view of what it looks like in terms of the TPS sensor and the sensor stack. So now on to the actual results that we measured using the titanium iron alloy metal hydride that has been provided to us by Jacques and the UQTR team. You can see here is the extensive data that we've measured in different conditions. So we've tested it under vacuum, under air, ambient air, under ambient hydrogen, and under high pressure hydrogen. So starting from step 1 on the line graph right there, the basic operation is pretty much the same as the TPS with some slight modifications here and there. But the basic principle is it's pretty much the same. The power input into the needle and the needle heats up, that heat transfer into your sample, and then we measure it as a change of temperature over time. Slight difference, or the main difference between the two methods so far is that it's a line source versus a planar source, and again, there's a different implications on how the math works and all that, but again, it's fundamentally similar in a way. So shown right here is our TLS high pressure cell on the left. It's about 50 millimeter in length, and again, the minimum volume is usually somewhere in the 60 mil total amounts. And you can see right there is an example of a metal hydride powder inside the cell itself. I believe this is magnesium in this picture. Yeah. So similar tests, or at least sets of tests, has been performed using this time just the powder form of the titanium iron metal hydride. You can see that at the beginning, though, we started measuring it in air. The value that we ended up getting was about 0.21 watts per meter Kelvin. And again, all that is a set of 3 or 5 data sets per condition.
Simplifying thermal conductivity.